Hi class, today we're going to look at section 7.7 and it's a very theory heavy section. So buckle up here. Before we get in, let's do a really kind of relaxing, easy little warm up that will set the stage nicely for our lesson today. It may take you a minute to remember how to find the inverse of a matrix. I know that it's been a while since we looked at that, so you might need to relearn that real quick. You can either wait and see me do it, or you can go look in your notes from earlier in the year. I promise we have done that before. The second one, my suggestion, my hint there would be to do 2, 0, 0, negative 3, that matrix, times itself, like just once, right? Like, so do it squared, not to the fourth power. See what happens there, and then I think you'll see that taking the third and the fourth power, what is going to happen should become obvious, and this is a special matrix you'll see. So pause and try these two. All right, going through the first one. If we find the inverse of a 2 by 2, we're going to do 1 over the determinant, and so I trust that you can find the determinant of that matrix. The determinant is 2. So 1 over, it's always going to be like 1 over the determinant, and then you're going to do kind of a switch on all these elements here, right? These two elements get swapped. These two elements, the opposite of those elements is what you need. So if we want, we can bring in the scalar into the matrix, and there's the inverse. To verify that it really is the inverse, you can now multiply this, check it. Go ahead and do it. Check this times this should equal the identity, right? 1, 0, 0, 1. Give it a try. For the second problem, again, my hint, let's take a look at my hint. Let's not do the fourth power. Let's do the second power first and just see what would it look like to multiply this matrix by itself once. Multiplying diagonal matrices like these is quite easy and fun, right? Because what do you get? In this first row times this first column, to get the first entry will be just 2 times 2, that's 4, and then plus 0. And every time we do these, so the first element, I guess, is 4. And then in the second, now we're going to do the first row times the second column here. So that'll be 0 and 0. So it looks like we're getting this, yeah? And so already now I think you can probably predict what's going to happen. Because of the diagonal structure of this nature, normally taking square matrix to like the fourth power would be cumbersome. But here, is it really just taking each of the elements on the diagonal, so the fourth power? Yes, it is. You'll see both of these things needed in our lesson today. They're going to come up. So today we're going to take a look at section 7.7. We're going to discuss something called the fundamental matrix. We're also going to talk about some other important ideas from linear algebra that are going to tie into what we've been doing here. So again, today's really more theory. Yeah, I think some of it has some application, but don't get too bent out of shape if you don't follow every symbol here. There's a lot. This is dense. I'm just warning you. So let's first introduce the notion of a fundamental matrix. It's pretty easy to say what that is right out of the start here. So let's say we have a system and we've already found the general solution using our eigenvalue eigenvector method. So I trust that you can find that. If you want to verify that, feel free to pause and go ahead and do that, but it is the solution. The fundamental matrix then we define to be this matrix, and notice that what we're doing here is we're putting in the rows, we're multiplying. It's like the fundamental solutions here. This is e to the 4t times this vector, and e to the 3t, the other fundamental solution, times this vector. So that's what these two columns, how they appear there. You'll see here that we're using a new Greek letter. We're using psi, so we're going to use that to denote the fundamental matrix. Now, to be fair, I think you would agree that the fundamental matrix, we really shouldn't say the fundamental matrix. We should say a fundamental matrix, like it says here. And the reason is, first of all, well, you know, it goes without saying that those eigenvectors could have been chosen differently. We could have used, remember when we made these choices here? Now the eigenvalues are going to be what they are. But the eigenvectors, we can choose instead to have any scalar multiple of these vectors. And that could have been loaded in there. And actually, it's even better than that. We could have also done kind of linear combinations of these two solutions. So, and those would have formed a fundamental matrix too. So I just want to make sure we're clear. This isn't the only fundamental matrix. This is one that operates, though, as a fundamental matrix. So if it really is the fundamental matrix, then and it has fundamental solutions in it. Remember what we mean? We've always meant by the word fundamental solutions. We mean here that the solutions are linearly independent. In this case, we have the columns are linearly independent. We have that the determinant will not be 0. Also, think about all the stuff you know from linear algebra. This is non-singular. That is, this matrix I have in front of you right now, it has an inverse. And again, I'll just emphasize that it's not unique. But the one thing that's kind of cool about the general solution is that we can, or excuse me, the fundamental matrix, is that we can write an initial value problem very compactly now, right? We can write, if we use this psi matrix that we have written down, and we consider the constants to be their own vector, just verify that the thing we have up here can be rewritten in this yellow box as what we have down here in this yellow box. Just this, x equals psi of t times the vector of constants, c. And that kind of nicely, compactly summarizes an IVP, right? We're looking for once we have we'll solve for that constant matrix. I shouldn't say an IVP, but it's like a nice, quick way to write the general solution, I should have said. We'll get to IVPs now. So imagine that we do impose some initial condition. By the way, I have some boxes up at the top just because we're going to work with those numbers in this example, and just to kind of a nice summary of what we just did on the last slide in these boxes. Okay, that's why they're there. We might need to refer to some of those numbers and those symbols as we move through this. So imagine that we had these, what someone might consider to be kind of maybe the most interesting and basic initial conditions. Let's imagine that we had the initial condition that we want x of 0 to be 1, 0. So solving that, here's our fundamental solution right here. Or excuse me, here's our general solution right here. And I'm going to plug 0 in. And so if I do, then this is what I get here. And I'm looking for like a C1 and C2 that will make this true. In the first equation, we've got C1 plus C2 equals 1. And in the second equation, I've got C1 times 1 plus C2 times 2 equals 0. Right? And now we have a system of equations. We can solve maybe even quickly in our heads. We can find that C1 and C2 for this initial condition here, that's the C1 and C2 we need. And of course, we can do a similar thing if I gave you this, and you'll find that in that case we need this. So okay, so now we've just kind of solved two IVPs. Maybe are you okay with me writing them the way I have here? What we have in the end are particular solutions, right? The solution is very easy to check here, right? That this solution satisfies the differential equation that we started with and the system of differential equations. And also, if you plug in 0, you'll get 1 here and 0 here. And over here, this one satisfies in red the initial condition x of 0 equals 0, 0, 1. If you plug in 0 here, you'll see you get 0 and 1. All right, so now we combine the blue and the red to form something called, this is our very special fundamental matrix, we'll call it phi. And here, this is there is only one of these. This is a special one because this is the only one that is a special kind of, it's still a fundamental matrix, but it's a very special fundamental matrix, right? Because if you plug in 0, you get the identity. That's one important feature of this. Now I want to summarize the work on this slide. You might, maybe I should have just led with this, but there is kind of maybe a better way to conceptualize all of this, and it has to do with something we saw in the warm-up. If we want it to be true that we get one that we want to end up getting, let's see, we want this times 1, 1, 1, 2, this matrix to end up being this, then we can figure out what this matrix, this special fundamental matrix is going to be by solving using the inverse here of this matrix 1, 1, 1, 2. And you'll notice that the inverse of this matrix just is these two things highlighted in yellow. Do you see that? 2, -1, -1, 1. And so that's the matrix that we have here. And you can see that when we do that, we multiply this by this, it's essentially doing all of the blue and the red work all at the same time. And it doesn't involve then having to solve these systems separately. I know they're easy systems to solve, but this is kind of a very compact way of doing all of the things that are hiding behind this box right now, all in one fell swoop. Just multiply this, our fundamental matrix, by this, the inverse of, well, this is the notation we want, right? It's our fundamental matrix psi times, I guess, psi inverse of 0, right? So notice that this is what we get if we plug 0 in to here. We get 1, 1, 1, 2, 1, 1, and 1, 2. And so we want like the inverse of that matrix if you plug 0 into it. I told you this was going to be dense, but hopefully you follow that. We're now going to use that in the next slide too here. So this is a very special fundamental matrix. It's a little bulkier, but you're going to see that it has a really special property we're going to look at in just a second. So why is this so special? Why spend all this time and all this heavy theory? Whew. Okay, just to summarize, I brought all this back over from the other slide. Okay, we've got our phi special fundamental matrix. And the powerful thing about this is this particular matrix, this particular fundamental matrix, is that it can instantly solve any IVP for this particular general solution. For this general solution, we can, if you give me some initial conditions, then I can solve it. And then if you say, actually, I wanted these initial conditions, you can solve it right away too. So for example, let's say we want to solve this system with these initial conditions. This can be accomplished by simply multiplying the fundamental matrix, the special fundamental matrix phi here by 7, 3. So notice here, this is not the initial conditions that we haven't mentioned this at all yet, right? So any initial conditions you want, you could put here, and then you multiply this by this, and it just gives you the solution to the system subject to those initial conditions. It's easy to verify there that if you plug 0 in, you get 7 and 3 in the top and bottom of that. But it's also pretty clear that that's going to solve that has the form, doesn't it? Doesn't it have the form of our general solution? It's like linear combinations of e to the 4t and e to the 3t. And linear combinations of e to the 4t and 2 e to the 3t, right? Like it has to be in those proportions, that recipe, that mix. So hopefully that makes sense. So the proof of this fact, this remarkable special fact that I'm just taking advantage of, is the following, right? We're saying if you were to take, what would happen if you took our special, we said this is the kind of the normal way of writing down our general solution. And if we have an IVP, then x of 0 we're demanding be equal to this, right, where we plug in 0 times some constant. Solving for c, the constant vector, I mean, isn't that what we want to do when we're solving an IVP? We want to solve for the constants. And the constants are being stored in that vector, remember. This is kind of a nice, quick way to summarize way up here our entire initial value problem, or our general solution, right? If we have 0 in there, though, it's an initial value problem. We're like solving for the constants. So now c is equal to, if I just multiply on both sides of this equation by the inverse of psi, inverse of this fundamental matrix, then I'll get this. And now I can take that and replace it back up here in this equation that we just were writing. All of this nonsense in blue is c, apparently, right? You see the substitution I made? But now, wait a second. This part right here should look very familiar. Psi of t times psi inverse of 0. That's our fundamental, our very special fundamental matrix phi. So, okay, but again, just to summarize, what does this say? Well, it says what in symbols here, what we just did here. Well, I guess I have it here as well, right? Is that what we're saying is if you can lay hands on, if you can create this fundamental matrix, then to solve the IVP, you just multiply by the initial conditions you want. In this case, 7, 3. But it'd be very quick and easy to multiply by another set of initial conditions. All right, so let's work through another example and see if we can't find that matrix phi of t. So I'm going to do it again. Well, I'll do it one way, and then I'll mention the inverse idea too. Okay, so first of all, this is in our 7.5 lesson, so we'll just pull again, feel free to double check this, but there's the eigenvalue. There are the eigenvalues and the eigenvectors. Yay. Okay. So then that means a fundamental matrix would just be this, right? Again, I'm just multiplying like we always do, this blue vector, this eigenvector, times e to the negative 4t. So that's the blue, and e to the, and then it'll be e to the t times e to the 3t, and negative e to the 3t for red, right? We're going to multiply this vector by e to the 3t. So there's, I guess it says find a fundamental matrix for the system. So we did that. But then it says also let's find the special fundamental matrix phi that satisfies 0. If you plug in 0, you get the identity. So notice right now that that's not true of this particular fundamental matrix, right? This is a fundamental matrix for the system. It's got all the things we need. It solves the differential equation, the system of differential equations. But if you plug in 0, you don't get I. You don't get the identity. You can check there, right? You get 1, 1, negative 2, negative 1. So there it is, actually, 1, 1, negative 2, negative 1. What we want to have happen is we want to have it be true that when we plug in our constants here and multiply, we want it to be true that we get 1, 0, the first column of the identity matrix. You can solve that, and you'll see that you get that. And likewise, you want this to be true. And in order to get that, we can do that. But then we can also just do, I'll mention it in a second, but already I want you to be thinking, could you do all this? I'm phrasing this very much in the language of like systems of equations rather than using inverses, right? So maybe there's a faster way to do that. And so what we can do, think about how you could do that with inverse matrices. So I'll write this down now that we've found our constants that we need for this matrix. Negative 1, 2, and negative 1, 1 are going to get loaded in here. And so now when we multiply that by our fundamental matrix that we started with here, the generic one that we had, we're going to get the special fundamental matrix phi of t. Now, again, notice that this matrix right here is simply the inverse. We can get this more quickly than maybe having written what we wrote here, right? This is simply just the inverse of this matrix here, 1, 1, negative 2, negative 1, the one that if you plug 0 into this, you'll get this. So take its inverse. Now the inverse just happens to have a determinant that is 1. That's convenient because there aren't too many fractions then. But I promise these are inverses here. So that makes this actually pretty, maybe a lot faster, right? In order to get the fundamental matrix phi, you just need to take our matrix here. Again, this I think tells the whole story right here. Take our fundamental matrix that we initially found and multiply by the, you got to get all this, by the inverse of this matrix with 0 plugged in. Did you catch all that? And that makes a pretty quick process just through matrix multiplication. Do row by column. Let's just double check like the first entry, for example. E to the negative 4t times negative 1 plus 2 times e to the 3t. Do you see how that's the first entry? First row, first column gets us the first entry in the first row, first column. Check all 4 and verify that this multiplication does give us this fundamental matrix phi. Well, we have a couple of nice other pieces of theory here that we're going to talk about. We want to introduce the matrix exp of AT, or the exponential matrix. I don't know that anyone pronounces it that way, but the exponential matrix. A of t. This is kind of an interesting idea. I don't know if you're used to this notation. I think we did mention it maybe once already this year. Sometimes when we have something cumbersome, we'll write exp instead of e to the. All right, so before we talk about putting a matrix inside of a power there, look at that. What could that even mean? E to the to a matrix? Can you do that? It's maybe not something you're familiar with doing ever. So this is going to kind of, for the first time, answer the question, like, what does that mean and can we do it? But before we do that, just recall what we meant, but why this is even maybe a worthwhile question, why this might be coming up in what we're studying right now. Go back to the earliest part of the year. Do you remember that this is one of the most basic differential equations we've done, right? This is the exponential differential equation, right? It's just has the solution x, looks a little different here because of the notation I'm using, right? But the solution is just like x equals x0 times e to the at, right? That's all that means. So verify that. You can pretty quickly verify that that satisfies this initial condition. Of course, if you plug 0 in, you get x0. And if you plug 0, and if you plug in, and if you take its derivative and plug it in here, you'll get that. Okay, so we kind of maybe, I don't know, what do you think? Should it be true then that our matrix version of this with vectors, with this initial value problem, has this as its solution, x equals x at x to the 0? We're using this as a just as kind of a subscript here. That sounds really reasonable, given that we just like changed the font. You're like, okay, sure, Mr. Chase, I believe you. But what does it mean, again, to take e to the power of a matrix? So we have to kind of unpack this. The answer is yes, this is the solution. But what do we mean by that? Let's not get ahead of ourselves. So recall that the way we kind of thought through this in a calculus context is we expanded this in a series. E to the at is equal to one of the first power series you ever learned, 1 plus at plus a squared t squared over 2, right? I'm just expanding this in the e to the x power series, right? E to the t power series. We've got an at in there though. So maybe we can do the same thing with this set of symbols. That doesn't constitute a proof, it's merely a suggestion. So the exponential of a, this is a very attractive option for defining what we mean by the exponential of the matrix A times t, because we know how to take matrices to powers, right? That makes sense to us. We know what all these symbols on the right side of this equation mean, right? We know how to take a matrix to the third power, a square matrix to the third power, and multiply it by t cubed over 3 factorial. That's a scalar, so that all makes sense. So the next question is that what we really wanted, though? Let's just check, for example, one thing that we would want. If you differentiate this term by term, then you get the same series again, right? Times a. So that's nice, right? A is acting just like the chain rule does for normal constants, right? So that's the kind of the derivative we expect, and it does seem to satisfy then the differential equation as well, right? Because of that property, that in particular, that property. The book has a further discussion, but if this really is true, then not only does this solve our differential equation, but it also must just like be phi of t, the matrix that we were talking about earlier, because for an initial value problem, we know that we discussed back in, don't pressure me on this, section 7.2 or 7.3, we discussed a little bit of theory there that guaranteed for us a unique solution to initial value problems of this type. So we can't have two different things. This must also be the thing we've been talking about throughout our lesson. One last kind of fun piece of matrix theory that we can bring in here. We're going to discuss the notion of a diagonalizable matrix, and this is going to come up again and again in your linear algebra studies in the future. But this will be just the first taste of such an approach. So recall that in our example that we had been using, we had these eigenvalues and eigenvectors listed here. Let's let T be, capital T, be the matrix that contains as columns our eigenvectors, 1, 1 and 1, 2. And now also let's compute its inverse. And I think we already did that, but there it is again. The determinant, again, was just 1, so lucky us. And it turns out that this is the case, that if we take, this is a remarkable fact, just right out the gate here. It turns out that, notice there's something very fun about this. If you do T inverse, there's this guy here, times our coefficient matrix that we started with, we don't have it handy here, times this, that's the matrix that has these as eigenvalues and eigenvectors. I should have put it on the slide. Then you will get this matrix here. We'll call it D for diagonal. But notice the things that are on the diagonal are something special. They are, in fact, the eigenvalues that go with the columns that we started with for T. So this is kind of fun and interesting. There's a proof on page 418. So in our example, let's let x prime equal a times x. Of course, that's the problem we started with. But let's define y in the following way. Let x be equal to t times y, where t is equal to this matrix here. Okay, well then x prime, because t is just a matrix of constants, then x prime is just equal to t times y prime, right? Constants, constants, constants. And now let's make this replacement, both of these replacements here, right? So x prime is equal to ty prime, we just said, so I'm going to replace that on this side of this equation. And a times x, well, what's x? X we just defined to be ty. Now I promise I'm going somewhere with this. Now I can multiply on the left, on both sides on the left by t inverse. If I multiply on the left here by t inverse, this t inverse times t is the identity, and so we just get y prime. And if we multiply by t inverse on the left, on the right side, we'll have this expression, but t inverse at is the very thing we were just talking about. And so y prime is equal to d times y. Interesting. And now we can return, there it is. And now we can return to, so now we can do this, right? We can say, well, y is going to equal the exponential dt. You might be thinking, okay, well, isn't that kind of what we wanted to start with? But here's the thing. Taking powers of that matrix is quite easy, right? It's just going to be, if we do the power series for this, it's just going to be the power series for each of these, because every time we take those to various powers, see the warm-up, part B of the warm-up, right? We're just going to get powers of our number 4 as we go out, and our number 3 in the numerators of that exponential expansion. So you're just going to get 2 copies of power series for e to the 4t and e to the 3t. So that's nice, right? And now we can get, by taking this back to x, we can get our fundamental matrix psi. And that's the same one that we obtained on an earlier slide. Go back and take a look. So I just wanted to kind of end with that discussion of diagonalizable matrices. I think that's kind of fun and interesting, and it ties things together nicely. So again, lots of theory here. How will we test this? Well, do some of the homework problems. I think, yeah, I'd like to be able to ask maybe some basic questions about this, but again, maybe don't stress too much about all the notation. There is a lot here. I recognize that today's lesson was dense. So thanks for hanging with me, and we'll see you next time.